Okay, you guys. So in this part of the lecture, we are going to discuss Dave MacMillan's work. And in the next following parts, we'll introduce organometallic chemistry. So let's just dive into Dave MacMillan and his contributions. Now, when it comes to Dave MacMillan's work, he uses organic molecules as catalysts. And this is really different from David Evans and Andy Myers, where the oxazolidinones and the pseudoephedrins were used in either excess or in one equivalence to introduce chirality into the products. Dave MacMillan says no, you can use organic molecules that are chiral, introduce chirality into your product, and you can use them as catalysts. So you need less than one equivalent of this chiral molecule. And this is known as organocatalysis. And Dave MacMillan is known as one of the pioneers of organocatalysis. There is a beautiful paper in Nature where he describes organocatalysis and how it's so much better than organometallic chemistry or transition metal chemistry. It's a really quick read and it's a really interesting read. And so because he has contributed so much to organocatalysis, he actually won the Nobel Prize in 2021, so just recently, in chemistry. And so why is this such a huge achievement? In chemistry, usually the Nobel Prize goes to a biochemist, right? It is still chemistry contribution, but it's usually bio-related. And so when Dave MacMillan and Benjamin List won the Nobel Prize, it was on organocatalysis. It was a contribution to organic chemistry. And a lot of this work was done at Caltech, but he is now at Princeton. Okay. If you go into Dave MacMillan's website under his publications, he provides you with all the PDF versions of his publication, which is really rare. So even if the university doesn't have access to those publications or to those journals, he's provided PDF versions of everything for you. So it's really nice to go in there and to read a lot of these articles. Now, Dave MacMillan, we'll talk about Dave MacMillan's work, and what we'll do is just first review a lot of Chem 124 material before we jump into it, because Dave MacMillan's transition states and intermediates aren't as complicated as the oxazolidinones and the pseudoephedrins. It's actually pretty straightforward, but it does require that we review some Chem 124 material, okay? So a couple of things that we'll be reviewing first before we jump into Dave MacMillan's work. And the first thing that we'll be reviewing is aldehydes, specifically alpha beta unsaturated aldehydes. Okay. And so if you remember from Chem 124, when you add a Grignard to any aldehyde, whether it's alpha beta unsaturated or not, these Grignards add to your carbonyl, followed by the addition of water to protonate, and you get an alcohol. And specifically, because you already have a group on your aldehyde, and you're adding a new group, you get a secondary alcohol. So nothing new. The only new thing that you learned when it came to these alpha beta unsaturated systems is that this product is known as the 1,2 product. And it's known as the 1,2 product because you need to number your conjugated molecule, and you always start at the oxygen. And so oxygen is always 1, and you number from 1 to 4. Again, you're numbering the conjugated part of your molecule. And since your alkyl group went to carbon 2 and you're protonating oxygen 1, it is known as the 1,2 product. Okay, so that's a quick review of what's going on. Now, you also learned that you can form 1,4 products. But this was specific to ketones. So if you have a conjugated ketone, we do the same thing that we did before. We number our conjugated part of the molecule, giving oxygen 1. And if we add Gilman reagents, you remember Gilman reagents, add to carbon 4. And I'll continue to number. Once you add water, you protonate carbon 3. And you form what's known as your 1,4 product. And it's known as 1,4 because your nucleophile, is attacking carbon 4. My electrons go all the way to oxygen 1. And if you remember from our very first lecture, oxygen cannot get protonated, even though it has the negative on it. And the reason for that is because the formation of the carbonyl is a lot stronger than the formation of the carbon-carbon double bond. And we talked about that in our first lecture. So this is known as the 1,4 product. And you learned this in Chem 124. Now, the thing about this is that this is specific to ketones. Aldehydes, unfortunately, do not do 1,4 product formation. Aldehydes cannot do 1,4. But ketones can do 1,4. Now, ketones can also do 1,2. So why can't aldehydes do 1,4 product formation? And the reason for that is pretty simple. The reason for that is because when you have a nucleophile, this carbonyl carbon is the most reactive. It's easy to access because that hydrogen is so small that it doesn't block the entrance of the nucleophile. So if the nucleophile has to pick a place to attack, it will always attack the carbonyl carbon. It's easier access. Ketones can do 1,4 because depending on the R group, the nucleophile will favor adding 1,4 if the R group is bulky, right? And so we learned in 124 that aldehydes are always more reactive than ketones. Always. And the reason for that is sterics, as we just explained. Hydrogen is small, and nucleophile can add into the aldehyde carbonyl. Okay? The other reason is electronics. So what do I mean by that? And I'll draw an aldehyde and a ketone version. We have resonance for both of these. I'll draw my resonance and I'll show my flow of electrons. Okay. Please notice that this is a tertiary carbocation, while this is a secondary carbocation. Notice that it's a carbon with 2 substituents as opposed to a carbon with 3 substituents, right? Because this is a tertiary carbocation, it's more stable. Because this is a secondary carbocation, it's more reactive. So a nucleophile can add to my carbonyl carbon more likely than it can add to my ketone carbonyl carbon. So because of sterics and electronics, aldehyde carbonyls are super reactive and nucleophiles always add 1, 2. Always. There's no ands or buts about it. Okay? So that's the first thing that you should note. Dave MacMillan figured out a way for aldehydes, specifically alpha beta unsaturated aldehydes, to give 1,4 products. And so that one reaction is literally what won him the Nobel Prize. And he did such a beautiful job at figuring out a way around this reactivity and the sterics in an aldehyde. So again, before we move on, we still have to do a little bit of review. I just wanted to introduce the impact that he had on alpha beta unsaturated systems. So review number 2. This is still Chem 124 material, and then we'll bring it all together. Imine and enamine chemistry. Now, imine-enamine chemistry is specific to aldehydes and ketones. Okay? So if you remember from Chem 124, if you have an aldehyde and you treat it with acid and a primary amine meaning one R group on your nitrogen, you will always get an imine. And ideally, you were taught the mechanism, right? If I treat this with an acid under acidic conditions, I usually tell my Chem 124 students, you will never see negative charges. You protonate your carbonyl oxygen. You add your nucleophile. You do a proton transfer. Hopefully this is coming all back to you. You can kick off water. The nitrogen lone pairs can help it out. And you form the precursor to the product you're trying to form. Because you've used acid as your catalyst, you need to regenerate it. So you take the conjugate base that you made, and you regenerate your acid. And you form your desired product. Okay? Hopefully, you also learned that the reaction is reversible. And when I teach this reaction, I tell my students, label your starting materials and your product. Because even though now we're going to do the reaction in reverse fashion, the intermediates are exactly the same and in the same order, but going backwards. So let me explain. Because the reaction is reversible, everything that was once product is now starting material. Everything that was once starting material is now product. So I'm going to start off with writing out my starting material, which was once product, my imine. Okay. And everything that was starting material is now product. Please also notice that my amine was my starting material, so it is now my product. Okay. Please also notice that I formed water, so that is now my starting material. And my acid, because it's regenerated, it is also part of my starting material. And so now I start numbering this as 6 and 1. And we are just going backwards, right? So just like before, zoom in so that you can see in the presence of acid, the first thing that you're going to do is protonate your nitrogen. You're going to form your conjugate base, which you will need to regenerate your acid. And you have just formed structure number 5. And you can see that they look exactly the same. So this is just structure number 5. Your nucleophile comes in. In this case, it's water. Attacks your amine. And you have formed structure number 4. Excuse me, let me draw out my bonds a little bit better. Okay, I'll also redraw my water. So this now looks like structure number 4. So notice how it's the exact same molecules, but going backwards. So if you know the mechanism going forward, you know it backwards. Just like before, I need to do a proton transfer. And not surprisingly, I made molecule number 3. Finally, I generate my double bond and kick off my amine, and I have made my primary amine and structure number 2, which is my precursor to my product. And finally, I regenerate my acid by bringing in my conjugate base, and I'm done. So you guys learned in Chem 124 how to make imines and how to reverse the reaction. And you learned both mechanisms, hopefully. Okay? And this is specific to primary amines. Okay? 1R group on the nitrogen. And this works for aldehydes and ketones. Now, like I just mentioned, Dave MacMillan worked with aldehydes because they're the most reactive, and because they're the most reactive, they can't do 1,4 addition, so we're just focusing on the aldehydes, or aldehyde example. So now let's do enamine. This was imine. Now let's do enamine. And I'll use the exact same aldehyde. Oh, excuse me. But without the double bond. Acid. And for an enamine to be formed, you need a secondary amine. And if you remember, an enamine, En stands for an alkene, and an amine on the alkene. And so you treat this with acid, just like you did for an imine. You protonate your carbonyl, oxygen, you form your conjugate base that you have to keep track of because your acid is your catalyst. You add your secondary amine. The mechanism looks exactly like it does for a primary amine. You do a proton transfer. You kick off the water exactly like before. Now here is where things change if you remember. My conjugate base, my water, has to come in and deprotonate and get regenerated. The problem is that the nitrogen no longer has a hydrogen for me to deprotonate from. And so the most acidic hydrogen is now the 1 alpha. So my conjugate base still has to come in and deprotonate, but now it deprotonates from the alpha position to form your enamine and to regenerate the acid. Okay. This reaction is also reversible. And just like before, we're going to do the reverse. You can remove the nitrogen, and everything that was product is now starting material. Just like before, we formed water, and everything that was starting material is now product. Now, I know that in this example, there's no double bond here, but we'll talk about that because that's important that I didn't show you the double bond in this case, right? If I would have had a double bond in this case, then I can't deprotonate at the alpha position because it would be a double bond. But Dave MacMillan took advantage of that. And so we'll get into that. Let's just go ahead and finish up the reverse. Okay. And just like before, it's going to follow the same trend. Once you introduce the acid, it protonates the alpha position. I form my conjugate base that I'm going to need because my acid's my catalyst. And you can see that we have formed product number 5. I can now add my nucleophile, which is my water. And I have formed product number 4. I do my proton transfer. And I have product number 3. And then I can kick off my amine, and that gives me my secondary amine, but it also gives me product number 2, which is the precursor to what I want. And so all I need now is to, of course, regenerate my acid. So I bring in my conjugate base. So again, if you know the mechanism for going forward, you know it going backwards, same intermediates. And that always helped me. I knew I could rely on knowing one because I could figure my way out going backwards. Okay, so now let's put it all together. You learned that aldehydes are super reactive and they don't do 1,4, and we've reviewed imine and enamine chemistry. And so let's go ahead and put all of this together so we can discuss Dave MacMillan's work. Okay, so Dave MacMillan introduced what are known as imidazolidinones. And there are first and second generation of these molecules. And let me introduce the first generation. And then I'll introduce the second. They are now commercially available. And just like with Evans and Myers molecules, you also have the enantiomers. So this is the first generation. Again, these are enantiomers. Please note, there's only one stereocenter. And then second generation, look pretty similar, just with different substituents. And two chiral centers. So please notice that in this case, there are two chiral centers. Okay. And so these are the four imidazolidinones, and you can make all four of them from S-phenylalanine or R-phenylalanine, which is an amino acid. Okay, so you can make them from amino acids and acetone. So really cheap to make. And so it isn't a surprise that they are now commercially available. They are super inexpensive, which is really nice. And so he made these two generation of molecules and uh, was able to control the stereoselectivity of 1,4 additions to aldehydes. So let's go ahead and jump into that. So first things first, let me introduce our alpha beta unsaturated aldehyde. He introduces the catalyst of choice. I'll use the following. So a couple of things that I want you to note before I go into the mechanism again. This is a secondary amine. Now, remember, secondary amines give us enamines, right? Which is impossible, like I just mentioned, because we've got a double bond already on there. Okay. So just make sure you remember that. And he uses hydrochloric acid as his acid catalyst. So the mechanism isn't really going to change, at least the very beginning of the mechanism isn't really going to change. Just like before, he adds his catalyst, his acid catalyst, and protonates the oxygen. Nothing has changed from what I taught you. Now he introduces his catalyst, which is a secondary amine. The only difference between this and what I've taught you is that it's a bulky catalyst. And not only is it bulky, but it's got stereochemistry. It's the nitrogen that's secondary. This nitrogen is tertiary. It's not going to attack. It attacks just like before. Excuse me. And we've introduced our nitrogen. Okay. So it's a pretty bulky group. Just like before, we're going to do a proton transfer, exactly like I taught you, or we were just reviewed. Because I want to make sure that I form the water molecule that needs to come off. You won't have to draw a six-membered ring transition state. Okay. Just like before, my water molecule gets kicked off. Okay. Now remember, this is where our acid catalyst comes back in and deprotonates to get to regenerate the acid and to get my enamine. But I can't deprotonate. I can't deprotonate because that's a carbon sp2. It is no longer acidic. And so this is the intermediate that Dave MacMillan works with. This is, the intermediate that he's worried about. And this is known as an iminium ion. And so he does a couple of things. He can't form the enamine. This iminium ion cannot form enamine. And he does calculations on this iminium ion. And there are actually two possible intermediates to this. And when he does his Spartan calculations, he finds that the molecule can actually rearrange, this intermediate can rearrange in two possible positions. And so let me go ahead and show you. Again, it's not a chair conformation, so don't worry about it. Let me draw out the two possible intermediates. The catalyst hasn't changed. The only thing that has changed is that my chain that was facing to the right is now facing down. And that's just to avoid sterics. Or it can face the left side. Regardless of how you put the double bond, right? They're pretty much the same thing. Now, here's the thing. When they did their calculation, they found that this was the favored intermediate. And it was a favored intermediate because it was the lowest energy relative to this one. Okay. And what they found was that if you note these tert-butyl groups, if I redraw them, these are bulky CH3 groups. And because they're bulky CH3 groups, they're crowding your alkene, the alpha beta unsaturated part of your molecule. So what you want is you want the small hydrogen atom on that side where you've got the bulky tert-butyl group. Now, we've talked about phenyl groups before, and we talked about the fact that phenyl groups are actually small. They're pretty compact. You can use them on your boron to get your Z-enolate, but phenyl groups are actually small groups because they're so compact. You've got your carbon-carbon double bonds. They're locked into a six-membered ring. Pi system as opposed to a chair conformation. So there isn't a lot of sterics. So the substituent favors being on the side of the less sterically hindered position. So this is your favored intermediate. So now that they know that this is the preferred intermediate, they add the nucleophile to this intermediate. And so let me go ahead and redraw it to sort of prove my point. Once you add the nucleophile, and Dave MacMillan has written paper after paper on the number of nucleophiles that you can use. And I'll just give you a really brief list of all of these different types of nucleophiles. But what they all have in common is that the addition is exactly the same for all of these. They all go through the exact same intermediate. Now, a couple of things. Please notice that this is still a conjugated molecule, first of all. Please notice that just like before, we can number this from 1 to 4, starting at the electronegative atom, in this case, the nitrogen. And the nucleophile, in this case, favors adding 1, 4. So nucleophile prefers to add to carbon 4. Why? Well, the first reason number 1, carbon 2 is sterically hindered. This group hinders the addition of the nucleophile to carbon 2. So the bulky imidazole, excuse me, not imidazole, imidazolidinone, blocks the entrance of the nucleophile to carbon 2. And so reason number 2, carbon 4 is not sterically hindered. And so it can add to carbon 4. It actually favors adding to the next electrophilic carbon. Okay? So my nucleophile doesn't want to add to carbon 2 because that huge imidazolidinone is blocking carbon 2. Now, the other thing that you should note is that the nucleophile attacks from the top. Because my benzyl and tert-butyl group are blocking the back. So notice how the back is being blocked by my bulky groups. So now my nucleophile wants to attack from the front or the top, however you want to call it. So once it attacks from the front, it does the same thing that we typically see for 1,4 additions. And what you get is follow your arrows, and I'll continue to number this so that you can see where everything is. Again, since the nucleophiles come in from the top, my nucleophile is now wedged and my hydrogen is now dashed. And I have formed an enamine. Notice how that enamine that I just formed was formed from the nucleophilic addition to the 1,4 conjugated system. Now that I formed my enamine, we know how to get our carbonyl back. We just talked about it. So let me redraw this. Copy and paste. We just talked about how enamines can go back to the carbonyls using acid and water to form our aldehyde. And so now it looks like you have formed the 1,4 product, which is the same thing as if you want to draw it. Oh, excuse me, this way. If it's easier to see, it's the same thing. Okay. All I did was rotate. If you can't see that, please come see me. I can help you see it three-dimensionally, but it stays as is. So he was able to reroute the reaction to form the 1,4 product, which had never been done before, ever. And not only was he able to do it with obviously this enantiomer, if you have the wedged enantiomer, then your obvious nucleophile is going to add from the back as opposed to the front, right? So you can get both products. And he got them in really high enantiomeric selectivity and high yields. The beauty of it is that he didn't just try one nucleophile, he tried a number of nucleophiles. So and I'm just going to list a couple of these reactions for you. MacMillan. Reactions. He tried EAS reactions. So from Chem 124, if you remember, electrophilic aromatic substitution reactions. He tried various substituted aromatic systems. I'm just drawing the line to the center because the R group can be anywhere on the benzene ring, or there can be more than one R group. He tried it with the more popular alpha beta unsaturated aldehyde, which is cinnamaldehyde. And it hits catalysts. Second step is acid and water to regenerate the carbonyl. And he, of course, got the 1,4 product. I want to say that not only did he try it with uh, phenyl aromatic groups or benzene aromatic groups, he also tried it with other aromatic groups. If you remember, benzene isn't the only aromatic system, it's just the most popular. He tried it with pyrrole as his aromatic. And again, got the 1,4 products. And please remember that anytime you do an EAS reaction, you always regenerate the aromaticity of your ring. And so he got the 1,4 product and regenerated the aromaticity of his nucleophile. He also did indole alkylations. EAS, where he uses indoles as his nucleophiles. And I'll use the same cinnamaldehyde as I did before and the same reaction conditions, the same catalyst so that we can stay consistent. Same as above. And please notice, indoles are also thought of as aromatic systems. Oh, excuse me. I drew it on the wrong carbon. I apologize. Notice how that's the carbon that's nucleophilic and that's the carbon that attacks. Also notice how you regenerate the aromaticity in your product. And you get the 1,4 product. He also used amine nucleophiles. And so what you'll see in a lot of his papers that he uses cinnamaldehyde because it's cinnamaldehyde's really cheap. He also does Diels-Alder reactions. And again, I'm just introducing a few of these reactions. I haven't even begun to go over everything he has done. He does Diels-Alder reactions because if you remember, Diels-Alder reactions are great when you have electron withdrawing groups. Just really super clever on how he figured all of this out. If you'd like to talk more about these, feel free to stop by or check out his website. He gets the endo product. Excuse me, not the endo product, the endo of the carbonyl and the exo of the alkyl or phenyl group. He also is able to add enolates. So once he gets carbonyl systems, he can deprotonate them with LDA, which is what we typically do to form enolates. And he adds them to cinnamaldehyde in the presence of his imidazolidinone, so same reaction conditions as above. Just really clever, everything that he was able to do. He's also able to add hydride sources. He's also able to epoxidize these alkenes. So reduce with hydride sources. And by reduce, I mean add H minus 1,4. Epoxidize alkene. Just really clever doing everything. And so you can see why he won the Nobel Prize, was able to deviate the reaction and give the 1,4 product. Okay, I can go on about Dave MacMillan. I won't. I'll stop here. Just make sure you understand the 1,4 addition. Make sure you understand how his catalyst forms and how you can take it off, how the nucleophile adds, and how it depends on the substituents on the catalyst, which is something that we saw in Evans. We saw it in pseudoephedrins as well. And this will be the last that we talk about organic molecules. And our next part of the lecture will move on to organometallics. Okay.